would look like this. So there you have it. We've covered hydrohalogenation, the classic acid catalyzed hydration, which in certain circumstances can involve carbocation rearrangements, so can hydrohalogenation for that matter. We've looked at a hydration process which is Markovnikov but does not give rise to carbocation rearranged products, the oxymercuratio reduction sequence. And finally, we're going to wrap things up by looking at yet another hydration reaction. A third, hydroboration oxidation. This one's different. This one's different in almost every way. First of all, it's anti-Markovnikov. It's not Markovnikov. And what do we mean by anti-Markovnikov? Well, we mean in a Markovnikov process, if I had a substrate that looked like this, the hydrogen would go across the less substituted and the OH across the more. Anti-Markovnikov is going to go in exactly the opposite order. Now it is called a hydroboration oxidation sequence, and once again it's going to be a two-step sequence. We need borane, BH3 in the first step, and we need hydrogen peroxide in the presence of aqueous basic solution OH- in the second step. There's my two-step sequence. Once again, if you don't have the 1 and the 2, it's wrong, because without the 1 and the 2, it would imply that you're adding borane and hydrogen peroxide all at the same time. The hydrogen peroxide will actually destroy the borane and there'd be no reaction. It has to be a two-step sequence. You've got to react it first with borane to form an organoborane, and secondly with hydrogen peroxide to oxidize the carbon-boron bond. Must be two steps. If you follow that sequence, you will do a hydration. It will be addition of H and OH, but it's anti-Markovnikov, which means the hydrogen will actually add across the more substituted carbon, and the OH, there's the hydration there, we've added H and OH, the OH will add across the less substituted carbon. It's anti-Markovnikov, can't emphasize that enough. It's also an example of a syn addition, so there's some stereochemistry here which we had not seen with some of these other reactions. By syn, I mean that both the H and the OH have added to the same face. So if you look carefully, both of them have added to the front face here. This compound I've drawn is chiral. It's optically active, so I've seemingly broken one of the fundamental rules that we've been talking about lately. If you start with an optically inactive starting material and react it with optically inactive reagents, you cannot possibly produce an optically active product. So what's going on here? Well, it turns out that the H and the OH could just as easily have added to the backside. In other words, I'm going to draw the H and the OH on the back. This methyl group's going to get kicked to the front. It's still a syn addition. The H and the OH have added syn. It's still an anti-Markovnikov hydration. Hydrogen is added to the more substituted, OH to the less. Both of these products form with equal likelihood, and they are a pair of enantiomers. So what I'm showing here is a racemic mixture, which I abbreviate with RAC in brackets. Now when you show the product of this in a predict the product type problem, you don't have to actually draw both of them. You can just draw one of them, it doesn't matter which one, and write RAC underneath, and that tells me that you understand that you cannot produce an optically active product from an optically inactive starting material and one reaction that involves optically inactive reagents. So several things to note here. Anti-Markovnikov, that's our first reaction that is anti-Markovnikov, and syn addition of H and OH. It is still a hydration. When you see hydroboration oxidation, you got to know those two things, anti-Markovnikov and syn addition. All right, a good question would be, why is it a syn addition? Well, notice that in the first step, it's a hydroboration reaction. We're adding borane across the pi bond. It turns out that when borane adds across that pi bond, the borane can either come from the top or it can come from the bottom, but it's going to come from either the top or the bottom. in a concerted reaction. And in this concerted reaction, the borane behaves as though it is sensitive to sterics, and the boron of the borane always adds across the less substituted carbon. The way we would show this aeroformalism, we're going to form a new carbon-hydrogen bond there using these pi electrons. Notice the pi electrons are pointing to where the bond will be, and we're going to form a new carbon-boron bond right there using those electrons. Once again, the electrons are pointing to where the bond will be. In this first step, this is the first step of a two-step sequence, it's a concerted reaction. This new bond to hydrogen, this new bond to boron are being formed at the same time that this boron-hydrogen bond is being broken. So there's a lot of bond making and breaking all taking place at the same time. That's concerted by definition. I'm going to pretend that my borane is coming from the top. If it's coming from the top, then both the new carbon-hydrogen and the new carbon-boron bond will be on top. There's my syn addition. The reason it's syn is because it's concerted, because both of those bonds are forming at the same time. The borane can come from the top or it can come from the bottom, but either way, in a concerted process, the new bonds will be formed on the same side, syn, with respect to each other. In the second step of this hydroboration oxidation sequence, we selectively oxidize the carbon-boron bond without changing the stereochemistry, and so that's why we still have syn addition of H and OH. So it's the second step which gets rid of the carbon-boron bond, replaces it with a carbon-OH bond, or carbon-oxygen bond, as part of an OH group. But it does so without changing the stereochemistry, so it's still a syn addition. That's important. So that's how you get the syn addition product. Okay, we've covered a lot of ground here. Let's just look at a couple of examples involving hydroboration oxidation. Here's an alkene. I'm going to run a hydroboration oxidation sequence on it. And what you need to know is that because this is a hydroboration oxidation, it's anti-Markovnikov. The hydrogen will add to the more substituted, the OH to the less. The result in this case is that alcohol. Very interesting. Had you run a classic acid catalyzed hydration, you would have gotten a different alcohol. You would have gotten the Markovnikov alcohol. In this case, there's no chance for a carbocation rearrangement. Remember, it's not going to happen all the time. You might have to think your way through that. By thinking your way through that, if you protonate at the less substituted carbon, generate the secondary carbocation, is there a hydride or a methide transfer which would create a tertiary carbocation? The answer is no. And if you can't create the tertiary carbocation through a Wagner-Meerwein rearrangement, then you don't have to worry about them. So all you're going to produce here is the secondary carbocation, which is trapped by water to produce ultimately the alcohol at the secondary carbon. So the anti-Markovnikov process leads to an anti-Markovnikov product, which is different than the Markovnikov product. And yes, you could also have treated this thing with mercuric acetate in the first step. That's an oxymercuration, followed by a sodium borohydride NaBH4 reduction, which would also produce the Markovnikov hydration product, which looks exactly like that one. In this particular case, they both give rise to the same product because they're both Markovnikov reactions. There's no possibility for a carbocation rearrangement, so this one and this one look exactly the same. The only one that looks different is the hydroboration oxidation, which is the anti-Markovnikov process. Well, we're going to wrap this up by looking at just a couple of reactions here. I've got 1-methylcyclohexene, hydrochlorination, hydrobromination, hydroiodination. All three are Markovnikov reactions. They will involve protonation at the less substituted carbon to generate the more highly substituted tertiary carbocation, which will then be trapped by either a chloride, bromide, or iodide anion. Or in other words, my 3 hydrohalogenation products. Down here, I have an acid catalyzed hydration. Protonation at the less substituted carbon, generate the tertiary carbocation trapped by water. Initially that gives me an oxonium ion, but after I deprotonate it with another water molecule, I get the alcohol. I'm adding H and OH. It's a hydration reaction. No possibility for a carbocation rearrangements in any of these reactions I've shown so far because of the substrate we started with. It generates a tertiary carbocation right out of the gate. If you choose to, you could get to that same product using a oxymercuration reduction sequence. Those two look exactly the same because they are exactly the same, form the same product. The one that's going to be very different is the hydroboration oxidation sequence. It's going to be anti-Markovnikov. Notice that I show an anti-Markovnikov addition, hydrogen adding across the more substituted OH across the less. Notice I show it as a syn addition, and notice that I show that a racemic mixture forms rather than this one chiral optically active product. The racemic mixture is optically inactive, and the product slate must be optically inactive since I'm starting with an optically inactive starting material and reacting it with optically inactive reagents. Well, that's the end of part 1. I'm also going to give you a second video detailing some other reactions of alkenes and alkynes, but that'll be in a separate video.